So this is the last topic in this chapter 5 on transient conduction that I want to cover is numerical methods, the finite difference method. Let's jump into it. So how do we solve transient heat transfer problems using a numerical technique known as the finite difference method? Well, how did we start this chapter? We started by saying we're going to solve for transient problems, but we're only going to do temperature as a function of time. That was lumped capacitance. And then once we mastered that, then we moved to temperature not only as a function of time, but also space. And we looked especially at the semi-infinite material. And so what we're going to do here for numerical is the same thing. Start easy, slowly get to the harder. So what's the easy? You just have temperature only as a function of time. So as a review, what was the governing differential equation that helped us get the exponential solution, the transient temperature profile for lumped capacitance? Wasn't it something like the time rate of change of temperature? Multiply that by the volume, the rho, that gives us our mass of our object that gets dumped into material and specific heat. So either MC or rho VC. And then on the other side we had the HA T minus T infinity, the fluid temperature. And if the object is hotter, greater temperature than the fluid temperature, then it's going to be out of the system. And it'll tend to cool or lower the temperature with respect to time. So that's why there's a negative sign. That was our starting point, our differential equation. And we had an initial condition that T at time equal to 0 was some Ti. And we separated and integrated, and we got a solution that was something like temperature at all future times minus the fluid temperature divided by the initial minus the fluid temperature. So it's a ratio of temperature differences equal to E to the minus T over tau. What was tau? Our time constant, and I think that helps us understand and explain things if you use the time constant. Or you could just have E to the minus HAT divided by rho CV. And the time constant's the rho CV divided by HA. That would, you could see how that's linked to define the time constant. So we could plot our temperature as a function of time. Maybe here was our lower T infinity. Here was our initial temperature. And the plot would look something like that. What does that curve, that exponential curve give us? That gives us the temperature at every instant in time. Right? Time is a continuous variable. But now what we're going to do is we're going to look to solve for temperature only at the initial point and only at this node point, this time point, and only at this time point, that time point, and these are separated by delta t. They're time steps. So we'll only get a value. Hopefully it would agree with the analytic if we had analytic to compare with, and we would be able to then plot the particular numerical prediction or calculation and compare it with the analytic continuous distribution. So we're going to be looking for those. So you might say, okay, we're going to have the temperature at the first time. Let's start our counting at 0. And then we'll have our first time, then our second time, third time, etc. Okay. Well, right away, you might be tempted to say, I'm going to talk about the temperature after the first time step, and then the temperature after the second time step, and then after the third time step. But we just did numerical solution for steady state in a grid, and we numbered our nodes. And where did we put the numbering of our node? On T, we put it at the lower right corner. So it's like, excuse me, this parking space is reserved. You can't use it. For time, that's already used for the location, and we're going to get to the location in a minute. So you think about it, and you say, well, there's four total corners that people have used and still use in science and engineering. The lower right corner is the most commonly used as a subscript to denote, oh, this particular location or time. But which one would you prefer to use? Would you prefer to use A, B, or C location? A is the preceding subscript, or B, preceding superscript, or C, the after superscript, right? Which one do you prefer? We'll do a show of hands. A, B, C. C wins. And if you remember your numerical methods textbook, you probably open it up, they probably use the same thing. It's most common to put time up here and location down there. Where are we at in time as to the step? 1 step, 2 step, 3 step, 4 step. And where are we at with respect to location down there? All right. So what we're going to do before we get to a bunch of locations, we're just going to use it to do time. All right. So we're going to be interested in calculating. This one would be denoted T0, then this one T1, then this one's T2, then this one T3. Well, you can see the potential confusion. Somebody sees that T to the 3, they think it's T to the 3rd power, but it's not. It's just our third, after our third time step. Okay. Well, this is all good. Hopefully we have an analytic solution to compare a numerical solution with, and we will. But how do we get our numerical solution? This is a repeat of your section of your numerical methods class. And it ties it in. So we see an application. Maybe you even had this application in your numerical methods class. So what do? We come in here and replace. Let's write that ordinary differential equation like dt. d time is equal to, and let's just put a grouping, h, a, divided by rho cv, and then we have t minus t infinity, and then a minus sign right there, right? So what do? You replace that by a numerical approximation for the derivative. So we say that t at some p plus 1 minus t at p divided by delta t. Again, it's confusing because you have that superscript. What does that mean? That's an indexing. And now why do you not use I and j? Well, we want to use I and j when we get to the space. So let's avoid that. And so you just start looking for something else. And it's common in this book and common in maybe your numerical methods book to put a p up there. Let p be 1, 2, 3, 4. So that's all it is counting. Okay, and then we finish that out by is equal to blah, 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 brought down. The only thing is when we bring this down, minus HA divided by rho CV times T minus T infinity, we could put a P up here, but is our fluid temperature changing? No, so you don't even need to index that. You can just get rid of it. It's not going to change. It's a constant. But that temperature is changing. And so you have a choice. You can put P there, or you could put P plus 1. And right away, you see if you put a P there, that's the Euler Method difference. And if you put a P plus 1, this would be implicit. Okay, so what you do is you just start time marching through the system. Depending on how you want to set it up in Excel, we're going to set up a problem, and you could march time either to the right or down. If you march it down, you think, okay, this is our time step I. We'll start 0, or P, put P 0, then 1, then 2, and then the time would be 0, then it would be 1 times delta t, then 2 times delta t, the time steps. You start typically your initial condition for temperature, and then you modify, so you have the P, let me do this, clean this up a little bit. T at 0 is equal to T initial, and then T at the 1 time step would be that minus, well, it'll be T at 0 minus HA HA divided by rho CV times delta T times T at 0 minus T infinity. Again, we're not going to do this as P plus 1. We'll do it as P, T to the P, which is the previous values to get the next one. So that's all I did was rewrite this equation. And then for the second, T2 is equal to T1 minus HA delta T divided by rho CV times T to the 1 minus T infinity. That look familiar? And you just march through. All right. So this is a new Excel spreadsheet. And so what I need to do is I need to start putting in, typically you put in a bunch of cells for the data, basic data. And we're going to start with time. The initial time is 0. And time step, dt, would be some value, maybe 0.3 seconds, something like that. And then the number of steps would be, I don't know, let's do 10 steps. And with that information, I can probably come over here and put in our step. And that'll be 0, then 1, then 2, then 3, then 4, then 5, 6, 7, 8, 9. Let's go to 10 steps to demonstrate it. And I'm interested in the time in seconds. That's equal to 0 to start it. And you could just say grab that one and add to it our delta t. And if I do a F4, that locks it in, and then I can drag that formula down and it'll percolate throughout the system. And hopefully I did that right. So we would go out to 3 seconds in this simulation. All right. And then we have our temperature, and our temperature is going to be in degrees C. And we have some initial value. Maybe we have over here T initial in degrees C. And what do you want to start at? 25, 20? What's going to be our fluid, H, or T infinity? I don't know. We can change it. But I'm just going to put in a value, 95 degrees C. Then we're going to have properties. We're going to have our convection coefficient, H. What do you want to put for H? Pick one. I don't know. 50 watts per meter squared degree C. We can go back and change it, right? All right. How about our, we're going to work with a sphere. Do you want to put in the diameter, radius? What do you want to put in? Diameter. And you want to put it in millimeter. Students have a lot of trouble with this, so I'm going to go slow right here. Let's say I have a sphere of 10 millimeters, and then I want to do the diameter in meters. So I take that, I multiply by 1,000 or divide? Very good. I didn't trip you up here, huh? So there it is. And you know what? I'm going to just get the radius in meters, which is a diameter divided by 2. And so Excel helps me avoid trivial errors, or computers, if you just do a lot of checking, helps you avoid those. And we're going to have some mass density, RHO, and let's put 9,000 kilograms per meter cubed. And what about some specific heat? Let's put in 500 joules per kilogram Kelvin. Should I put in those units? I'm saying them, but I'm not typing them in, but usually I type them in. And then my thermal conductivity, I don't know, 50 watts per meter K. So I can calculate the volume of my sphere. Hey, what was that formula? 4/3 times pi times r cubed. There you go. I can get the mass of the sphere, which is the product of the volume times the density, rho. I can get the area of the sphere because I needed that one. What was my area of the sphere? 4, why 2 of those? 4 times pi times r squared. True? 4 pi r squared. Look good? Did I make an error anywhere? Is this large enough? Can you see it well? All right. I think I have most of these or all of them calculated. I can come over here and I'm ready to start marching through the simulation. So for the initial, I'm just going to grab that value right there to start at 20 degrees C. And now for that first time step, what was my equation? I get the previous time step's value. I subtract my convection, H, times my area, A. Where's my area? There. Divided by mass, divided by specific heat. Now I could put the mass specific heat in parentheses or just do it that way, right? HA divided by MC. Did I do okay so far? Multiply by my time step. Probably put a lock on that. Actually, I'm going to need to lock all these, right? So that when I drag the formula down, it doesn't mess it up. Times, did you write that equation down? Do you know what I'm trying to recreate? What do I need next? Temperature at the previous time step minus my T infinity, which is this T infinity, and I close parentheses. Before I move on, I probably want to do this. Did I make an error? I got a couple people say it's good. Give me a thumbs up if you agree that it looks good or you didn't see an error. Because there's no sense in me marching on if I have an error. And some of you know it if I do. Okay, now I'm going to lock in some values. What was that trick on F4? Did I tell you students show me more about Excel than I have ever learned by myself? Students come up afterward, hey, try this trick. It'll save you. You won't look so look clumsy next time you do this. Okay, that looks good for locking it in. So it looks like it'll go to 20.15. And if I grab that lower corner and drag, that'll percolate through, and maybe I want to clean up on these digits and stuff like that. Maybe put a few more over here. This is my numerical. This is the temperature in degrees C, analytical. We have a solution for this, don't we? What was that temperature? Well, the first one is just initial temperature. That's easy. But what was our equation? T, the fluid temperature, right? That is going to be plus T initial minus the fluid temperature times our exponential of minus our time of interest. We're marching away in seconds, divided by our time constant. And instead of typing it all out, I'm going to put my time constant down here. I know Excel is going to complain because I just divided by 0, but I'm going to put tau right down here in seconds. What was the equation for my time constant? Is mass times specific heat divided by our H divided by our area. That look right? Thumbs up if you agree. I got one agreement. 2, 3, 4.
You need to lock in tau in your equation.
I'm going to lock in tau in my equation. Thank you for that. So I'm going to lock it in right there. And now I'm going to drag that down. And I can try and put these all on the same number of digits or something, kind of clean it up. And we can see, yes, there's some difference between the numeric and the analytic. You could even do a little error column, percent error, numeric minus analytic divided by the analytic. I know it's in degrees C. I'm going to put it in percentage, and I'll draw that down. And we really need to look at some digits before we can find the error. That's a pretty small error, isn't it? All right, let's go back to this part. Boom, I have a problem. It says it's a 3.2 millimeter diameter sphere of copper. Well, if I already built the Excel spreadsheet, I mean, I'm kind of just going to come over here and start percolating in here. So 3.2 millimeter diameter. I'll come over here. Instead of 10 millimeter, 3.2. Boom. So if I wanted to, I could show that I have updated that one by changing the color. So I updated that. And it's copper. So I look down here. I have a row of 8, 9, 10. Hit return. And a specific heat of 385. See the units? And the thermal conductivity of 397. And I just updated all of those. Okay, let's continue. It has a room temperature initial of 25, so 25 instead of 20. Updated that one. Is suddenly subjected to a fluid with free stream temperature of 90. All right, so we'll update that one. And a convection coefficient of 80. 80 right there. All right. Let's update that. How long does it take for the center of the sphere to reach 40 degrees C? Well, if I focused only on the analytic solution, let me do that before I jump back into Excel. I would say T minus T infinity divided by T initial minus T infinity. The lump capacitance solution was e to the minus. And then you have the H A T divided by rho C V. Okay. Well, if they're trying to find out how long it takes, then I need to solve for T. And so this one is 40 minus 90 divided by 25 minus 90 is equal to e to the minus, and then all those parameters times that t, and I solve for that t. And then I would do this. I would say take the natural log of both sides, and so I'll have minus HA over MC times t equal to the natural log of 40 minus 90 divided by 25 minus 90. I would make sure I could get that natural log and it looks reasonable. And then t is equal to the minus MC divided by HA times the natural log of 40 minus 90 divided by 25 minus 90. For this problem, and when we do that, that comes in right at 6 seconds. Now, and what we have is we can input this, but we need to do our time steps such that we don't end at 3 seconds. Let's put our time step to be 0.6, and if we do 10 of them, we'll end at 6 seconds. We verify that our analytic solution does come in at 40 degrees C, right? And our numeric, we would say, well, our numeric's going to get in a little less than 6 seconds. If I did a little linear interpolation, what is the fraction? I usually do like linear interpolation this way. I'll say the fraction between this point and that point for 40. That would be 40 minus this divided by this minus that. But so if I said numerically what is that time at which it's equal to, temperature is equal to 40, it would be, it's equal to 5.4 plus this fraction times the time step. And so I'd say, oh, it's really not 6 seconds to 0, 0, 0. It's numerically, I would say, oh, it's 5.92. So, I mean, there's a difference between a numerical approximation and the numerical solution and the analytic. True? So there you go. Any comments or questions? Now we have another problem, and this problem includes the space. So in the interest of introducing the space, I'll introduce it in the context of let's solve a problem. and then walk through the building of the math. So you have a 0.12 meter thick wall, initially at a uniform temperature of 85 degrees C. Everywhere it's the same. Suddenly, one face of the wall is lowered to a temperature of 20 degrees C. That's just what happens. It's one face is lowered to 20 degrees C, while the other face is perfectly insulated. No heat transfer in or out. So what's happening is you have a hot wall. One face is lowered to 20 degrees C. There's a lot of conduction out that cold face, while the other is insulated. So if I wanted to plot this, I'd say, oh, here's my wall, right? It goes from 0, where it's insulated, out to 0.1 meter, or 0.12 meter, right? And I'm going to initially put in a temperature here of 85 everywhere. And then boom, it jumps at this face right here down to 20. And I would get some profile of temperature that would penetrate and then cool it. And if I waited a long time, what would the temperature everywhere in my wall eventually go to? 20 degrees C. True? Okay. Using the explicit finite difference technique with the 30 millimeter node spacing and a 300-second time step, calculate the temperature distribution after a time such that it's 45 minutes. All right. And for the wall, use this value of K, rho, C, and alpha. So what do you have to do is you have to come in and discretize your domain. You have to put nodes, and that's the location, just like we did for steady state conduction. That's the location you'll get temperature values. If you want them in between the nodes, you'll have to interpolate. But you'll put a node, a node, a node, a node, a node, such that this spacing, delta x, was given in the problem to be 30 millimeters, 0.030 meter. Okay. So if it's 30 millimeter or 0.03, and this entire length, L, is 0.12 meters. All right, so what we got is we have 1, 2, 3, 4, and just as I sketched it, doesn't 5 work? That gives you 4 spaces in between. So we have 5 nodes. We have to introduce a little volume for each node. And so cut in between is the standard procedure. And we're going to then have a volume associated with node 3. And I think maybe like this. And I think, okay, that's my volume for node 3. And then I take a look and I say, how about for node 1? Well, because it's insulated right here, can you see that the volume associated with node 1 is half of what it would be for node 3? Yeah, all right. Now, let's do this for every one of these before you jump on the computer, either MATLAB, Excel, or any other software. Do it by hand and get it all worked out. Do an energy balance by hand for node 3, an interior node. Then worry about the edge nodes. There's special cases typically. So if we do, what we're doing is we're going back to our governing heat equation, our differential equation, which looked like you had a rho C partial of T with respect to time is equal to K, second derivative of temperature with respect to space. That's pretty abstract to a lot of students. Just do this. We have a control volume, do an energy balance. If you do an energy balance, an E balance for node 3, it would be I'll have the density times the volume for node 3, the specific heat. I'll have how does the temperature for node 3 change with respect to time. I'll introduce that superscript at different time levels in a second. Equal to, we'll have a K, we'll have an area divided by a length, which our length for conduction transfer is delta x between the nodes. And we're going to have temperature at node 2 pumping heat into node 3. That's our conduction from 2 to 3. And we're going to have our Ka divided by delta x, temperature at node 4 pumping into node 3. just like that. So we've done this type of discretization before when we had steady state. It's just now I have the transient part. So if you wanted to, you could bring that rho CV over. And if you think about what is this volume for 3, is the volume for node 3 equal to some area times some delta x? Yeah, and so we could replace that right here. Let me do that. Area delta x. Get rid of this volume at 3. And notice that the areas go out. Areas in all 3 terms. So it's, otherwise do this. You have delta y, pick it to be 1 meter. Delta z, pick it to be 1 meter. And then you can have your nice volumes and your nice areas, but the same result will happen. All right, so now what we're going to do is we're going to get an equation like this. We'll put in, let me do it in a couple steps, T3 dt equal to, and then we're going to have the K, we'll have divided by rho C delta x squared. Does that look good? And then we'll multiply by T2 minus 2 T3s plus a T4. Did I do the math okay? Thumbs up? Okay, good. Then we approximate with the time, T3 at time level P plus 1 minus T3 at the previous or the current time level. You divide by delta T. You divide by delta T, and what I'm going to do is I'm going to throw that put that delta T up there. So I'll have K, what is K divided by rho C? A new property we already were introduced to. It's called alpha. We have delta T divided by delta x squared, like that. T2 at time level P minus T3 at time level P plus T4 at time level P. So T3 at the the new time step is T3 at the old time step plus all of this. Work it out by hand. Make sure you're confident before you implement in Excel or another software. Okay, what was this alpha delta T divided by delta x squared? It looks a lot like a Fourier number. Our Fourier number was alpha T divided by L squared. So we would call this our numerical Fourier number or discretized Fourier number or some other. It's not our global Fourier number. It's some numerical Fourier number. And that'll even make the equations look more compact. All right. Once you have an equation like this worked out for an interior node, you have to go to, let's say, node 2 or 1. If I do node 1, I only have conduction from 2 into it. And it's half the size. I think you can work that equation out. And then for this problem, what about node 5? Well, we had this space suddenly lowered to 20 degrees C. You can write the energy balance, but then you're just going to replace it by saying, you know what, I know the value of that temperature is always 20. I don't need to really use the energy balance at node 5 to predict the temperature at 5. We used the energy balance at 3 to get an equation to predict the future temperature at 3. All right, let's do this. In the interest of time, I'm just going to show you, if I can find it, an Excel implementation. And this was a modified problem out of the textbook. So as a function of time, either in minutes or in seconds, we can look at the temperature for each node, node 1, node 2, 3, 4, 5. 5's temperature doesn't change. It's always 20 as time goes down. But the others start at 85, and you percolate using the equations that were developed to come down. And you'll see then it changes, and there's your temperature distribution at the interior node, 61.6 degrees, 55.5, etc. All right? I'm going to stop here. I'm going to give a quiz, and next time we move into the next chapter,